Good morning. Today we'll be starting off with another topic of light in O levels physics. We'll be talking about what light rays are and what makes up a light beam. So we need to know that light firstly comes under the class of an electromagnetic wave, which means that light can pass through any medium. It can pass even through vacuum. That is the reason why light is able to pass through space and the sunlight is able to pass through the entire solar system and even reach the earth. So this means that light does not require a material medium to travel, unlike sound, which can only travel in the presence of medium. Now we come to light as a light source. Now, what is a beam? A beam, there is a single light ray, and when there is a collection of several light rays, they basically converge to form a beam. Now, the speed of light is basically the same. And if you compare it with the speed of sound, you need to know that the speed of light is significantly higher than the speed of sound. For example, yeah, whenever in a race, two athletes compete with each other, they always look for the sound of the gun. They don't wait for them to see the smoke arising from the gun which the person shoots in order to signify that this is the start of the race. Why? Because the speed of sound is greater than the speed of light, and the person will be easily able to hear the sound faster. Now we come to the properties of light, reflection and refraction. Now the main property of reflection is that you need to understand that the angle of incidence and then the angle of reflection are always taken along with the normal, and the normal is around at like a 90 degrees for with which the light ray strikes the surface. So now I've talked to you about how the angle of incidence and angle of reflection are all always equal. Then the number two key rule is that the size of the object from the mirror is always equal to the size of image from the mirror, which means that when a light ray strikes a mirror, for example, if the object is placed over here and the mirror is over here, the image or the reflection of it will be of the same distance from the mirror by which the object is. Now they've talked about the pinhole camera. You need to know that people who have myopia or have difficulty seeing objects which are far away, when you make them look from a pinhole, they are able to see better. Why? Because the light rays converge and they can see the light ray or the object more accurately. Now we'll talk about the properties on how a pinhole camera differs. The pinhole camera is first inverted, it's inverted and it's reversed. Now, why is it dimmer? Obviously, because a pinhole only selectively allows a certain amount of light rays to enter, unlike the normal eye, which enables the eye to view an object by light rays coming from all sides. So now what is the effect of making the pinhole camera larger? Obviously, if we make the camera larger, there will be more light rays which we will be able to penetrate through. So the sharpness and brightness of the image will be increased. Now, here are a few of the worked examples. What is the nature of light? We know that light is an electromagnetic wave. How do luminous and non-luminous objects differ from each other? Now, luminous objects are those which are able to generate light from themselves, for example, the sun. However, non-luminous objects are those which rely on other objects and they reflect light from other things. For example, humans or even the moon, it doesn't produce its own light. However, a lamp is considered a luminous object because even though it generates basically light from electricity, however, it generates its own light. So now I'll talk to you about the second part of this topic, which is the reflection and refraction of light. I'll just pause the video for a second. Now we talk about the reflection of light. I told you that the angle of incidence, for example, if it's 30 degrees over here, and they tell you to calculate the angle of reflection, it will always be 30 degrees as well. However, what they do in the exam is that they give you the angle over here or they give you the angle over here, and then they tell you to find out the angle of reflection. So obviously what you will do is that you can see that this is a 90 degree. So you will subtract the angle which is over here, for example, for just for the sake of practice, if it's 30 degrees there, the angle of incidence will be equal to 60 degrees, and consequently the angle of reflection will also be equal to 60 degrees. Now we'll talk about the laws of reflection. I have already talked to you about how the two angles are equal. Now, whenever a light ray strikes on the surface, if it strikes a regular surface, the light rays will be reflected on longer regular pattern, or a longer regular line. However, if they strike along a rough surface, the incident ray and the reflected ray will not be along a regular pattern. Now, this is a regular reflection, whereas this is a irregular reflection, as you can see. And this is a regular reflection, which you can see the light rays are incident ray and the reflected ray are exactly uniform to each other. Now, there are several use of reflection. First is the periscope. You would have seen were basically periscopes used on a blind side. For example, when you're traveling to the mountains and you see a blind turn, obviously, how can you see that whether there's a car coming from the other end? With the help of the periscope, when you look into the periscope shows the opposite side of the road, which you can't see. How this works is that there are different mirrors which are inclined at to about 45 degrees, and you can see that the light ray strikes from one mirror to another and eventually goes into the eyes of the person. So now, what is the difference between a real image and a virtual image? The primary difference is that a real image is one which can be formed on a screen, whereas a virtual image is one which cannot be formed on a screen. For example, a mirror image is a virtual image. Why? Because even though you're seeing yourself on the mirror, however, the image itself, it doesn't occupy any space whatsoever. Now, the characteristics of a virtual or a reflected image, these are repeatedly asked in the exam. You have to remember three words. They're always virtual, they're always upright, and they're mostly inverted. Now, this rule I talked to you about in the first part of the video as well. And this now you need to know that the mirror image and the object image are also always of the same size. Apart from the same distance, they're also always of the same size. And now what you will be told to do in the exam is that, for example, you'll be told to locate this image. You'll be given the object and you'll be given the person's eye. So what you will have to do is you will simply be have to trace the light ray from the mirror exactly the same distance in front of the object as it was in front of the mirror, and it will be always in a straight line. For example, the image cannot form over here, it will always form in a straight line over here. And for example, if this is 3 centimeters, the image will always be 3 centimeter away as well. Now, these are some other applications or children use. For example, a kaleidoscope. Kaleidoscope is also essentially the same principle of a periscope, and it uses multiple reflections and changing patterns. So now these are some of the review questions. If I've told you before as well that if the angle of incidence is 30 and the angle of reflection is always also 30, how does a periscope work? A periscope works by using two flat mirrors which are inclined at 45 degrees with each other. And these are some other questions as well. You can pause the video and try to solve them on your own. Now I'll pause the video and load the next. Now we'll talk about the refraction of light, or in other words, the bending of light rays. So you can see over here that what happens is refraction take or bending of light rays takes place when light travels from one medium to another. And there are two types of examples I'll tell you. For the first example, light travels from a denser medium to a less dense medium. For example, water is more dense medium, whereas air is a less dense medium. So what happens is you can basically just remember it easily by remembering it as, instead of dense, you can remember the word danger. That whenever light rays pass from an area of more danger to less danger, the light rays move away from the normal. You can see over here that the light ray has moved away from the normal. And if a light ray moves from an area which is of low density to an area of higher density, for example, from air to water, there will it travels from an area of low danger to higher danger, so it always becomes closer to the normal. So they've talked about the definition. The diffraction is the changing of direction of light rays when travels from one medium to another. And this is a base, you can see how a straw appears to be bent, although it's uniform and straight actually. However, it appears to be bent because when light rays travels from the water to the air, our eyes perceive it as bent. However, light rays always travels as a straight light. Now there are two angles of rules of refraction, just like two laws of reflection. The first law states that the incident refracted ray and the normal are always lying in the same plane. And the second is this formula, which states that the angle of incidence and the angle of refraction are always a constant. Now, this is a refractive, these all of formulas which are being used, which will be used in the numerical questions. Now, the refractive index is just defined as the ratio of light in speed of light in a vacuum denoted by C with the speed of light in a material denoted by V. Now, another things are for you to remember are that the refractive index of a medium is always greater than 1, which means that light rays always travels slowly in a medium which has a refractive index greater than 1. For example, they've talked about glass which has a refractive index of 1.5. So this means that the speed of light is slower in glass by about 1.5 times more slower than vacuum. Similarly, in Snell's law, there's another question in which the Snell's law relates the angle of incidence to the angle of reflection by n1 sine theta equals to n2 sine theta, whereas the refractive index n1 and n2 are the refractive indexes of respectively of the two mediums. Now, apparent depth. Apparent depth is a phenomenon in which, for example, when you view a swimming pool. So I was explaining to you that in apparent depth, for example, when you see if you didn't go in a swimming pool and you see the water as more shallower than it actually is, what happens is that due to this phenomenon, when light rays travels from just in the example of a bent straw, when light rays travel from water to air, they actually refract. However, the what happens to the eyes is that the eyes only try to see the object in a straight line. So the eyes see the object in a straight line from the object traveling from the object to the eyes, whereas actually the light rays have been undergone refraction. Now this is the correct formula to calculate the apparent depth, which is taken by the formula equals to the actual. You take the ratio of the actual depth divided by the apparent depth. Now you'll calculate I'll tell you the relationship between the refractive index and the wavelengths of light. There is a mnemonic called ROIC wave, which signifies the red, orange, yellow, green, blue, indigo, violet. So as you go from R to V, the wavelength of the light rays decreases. So do you need to note that the refractive index and the wavelength of light have the inverse relationship, which means that violet has the least wavelength and consequently, it has the greatest refractive index, which means that light slows both the post and violet color. Now, here are a few of the worked examples which can be showed over here. The angle of refraction, if the angle of incidence is 22 degrees, so n equals to sine I over sine r, you just plug in the values 1.6 equals to sine, you'll be able to calculate it with the calculator. And here you can see you'll be able to apply Snell's law. Now, which law you'll have to put in each situation, this only comes by practicing. You'll have to memorize all the laws and consequently in each situation you'll be able to apply the relative law. Now I'll come to the last part, which will be total. So now, what is total internal reflection? Total internal reflection is that when light rays travel in a denser medium, they basically reflect totally and they are refracted out of the medium. Now, the most important topic or the most important concept to understand total internal reflection is the critical angle. The critical angle is the angle of incidence in the denser medium for which the angle of refraction in the less dense medium is 90 degrees. And this is the formula sine n equals to 1 over sine c, or they've just changed the values and they've written sine c equals to 1 over n. Similarly, this formula can be written like this: n1 sine theta equals to n2 sine theta, whereby n2 sine theta represents sine 90. So basically this is the critical angle, the angle of incidence for which the angle of refraction is 90 degrees. This is a typical example. So now this is number one, the diagram number one, you can see the refracted wave. Diagram number two, this is a refracted ray which has critical angle. Now this is the total internal reflection, just like the definition said. You can see that the angle of incidence is greater than the critical angle for the angle of incidence for which the angle of refraction is greater is is greater than 90 degrees. That is total internal reflection. Although you can see that over here the angle of refraction is 90 degrees. However, over here the angle of incidence will be greater than the angle of refraction so that the entire ray goes back into the water. Now, some of the most used commercial applications are optical fibers or the telecommunication industry. You can see that how it has grown because why? How is total internal reflection used in optical fibers is that the in light rays cannot simply be able to pass through the fibers and thus the wastage of the light rays or the line losses and the transmission are minimized because the bundles are used to transmit light from totally inaccessible places, and thus the optic fibers are easily able to provide rapid communication between two places. Now, another use is to cut diamonds. You can all know that diamonds have their unique property of basically glowing or they have a sharp appearance. Now, what maximizes their sparkling appearance is that because diamonds have a very high refractive index, the light rays are unable to refract out of the diamond and they just strike again and again multiple times inside it. So this gives it a sparkling appearance. Similar is the case with endoscopes. Endoscopes are used in the GE or GERD patients in medical life, and in the case of periscopes, in which we talked about reflection and refraction, how drivers used it in the everyday places. So this is the concept of total internal reflection. I hope you got the basic concept. Now, how to apply which formula? For example, the formula is n equals to 1 over sine c. So in this question, only the critical angle has been provided to us. So obviously, we'll just use that formula at which only the critical angle is required. However, you can see over here, for example, this is also uses n equals to 1 over sine c. I wanted to show you some other questions which I'll be showing to you in the next video. Thank you. I hope you like the video.